bright young students. So in this presentation, I am not planning to bombard you with a lot of theory and equations. So rather than that, I'll dwell on the history of rocketry, where it started, how it started, and how the world progressed in the space transportation system, and where we are right now, and the progress of our nation on this area, and what the future holds for our nation. So this is the broad topic I'll be covering in today's presentation. So since the spectrum of people ranges from high schools to college, so I have kept the presentation very simple, and I'll be mostly sticking on to the basics. To start with, everyone knows what a rocket is, and the fundamental equation or the fundamental law that it follows is Newton's third law. Every action has an equal and opposite reaction. So a rocket has a propulsion system where hot gases are formed, and this hot gases gets ejected at very high velocities, supersonic velocities. And since all this gas are being ejected at very high velocities, naturally a reaction force is felt on the rocket body. And that's the precise reason why the rocket gets propelled upwards. And to get an idea about the speed of a rocket, the rocket, it travels at almost close to 8 to 9 kilometers per second. So a travel from Pune to Mumbai is less than 20 seconds in a rocket. So now you can compare, you will get a feel of the rocket speed. And another fundamental difference is that aircrafts, it travels through the atmosphere, so you have plenty of oxygen around, so you can take in oxygen and use it for combustion. But in rocket, it will cross the atmosphere. That is a von Karman line, imaginary line, which we say as the boundary of the atmosphere, that is around 100 kilometers. Beyond 100 kilometers, it's vacuum. So there is no oxygen, so you have to carry oxygen. And naturally, when you have to carry oxygen, you think about the size of big tanks and all. So it's so it will be very bulky. So we may have to liquefy it to take it to bring it to a form of liquid oxygen, or other fuels which has oxygen in it. So that fuel can be in either solid form or liquid form. That I will present in the subsequent slides. So these are the two fundamental differences between the rocket and an aircraft. Now, why do we require rockets? We have because there is a need to put an object in an orbit, and that orbit can be low Earth orbit, medium Earth orbit, or very large orbits like geostationary orbit. They fundamentally, we call it as the satellites. So these satellites has to be taken to an altitude of around 600 kilometers or 400 kilometers to maybe 36,000 kilometers, depending upon the type of the satellite and the orbit to which it has to be put. So naturally, how do you take? So natural question is, how do you take this object to that altitude and stay? And this has to continue to rotate around the Earth. That is as per the Newton's first law. If any object, it continues in a state of rest or of uniform motion until it is disturbed by an external force. So you put a satellite at an orbit, and if it propels forward at a particular velocity, in which the gravitational pull of that of the Earth on the body balances the centrifugal force, then it has to continue to propel forward. So that is a basic principle of an artificial satellite. But how do you take it to that altitude, that height? For that, You think of a person throwing a stone up in the air. It will fall back on the earth after taking a parabolic path. That you can, normally you when you throw a ball, it happens in the playground. But you keep on increasing the velocity. As you see in the top left figure, the velocity, the velocity at which it is thrown, it increases. Naturally the falling point, the point to which it falls, it changes from A to B, and finally it reaches a if it attains a velocity where the centrifugal force can balance the centrifugal the force of attraction, gravity, or the gravitational pull, then it will stay there. And if it is too high, we call it as escape velocity. The kinetic energy of that body, if it's too high, it escapes from the gravitational pull of the earth. So this is the need to have a rocket to take the satellites to the required altitudes and to eject it to the required velocity. Now, I am sure that most of you might have seen this rockets majestically going upwards, and anybody see that when he or she see that that sight of a rocket going upwards, they will get thrilled. It's every time we does a rocket launch, it's a very thrilling experience. But then there are a lot of challenges also involved in it. You think about an object, a device like a refrigerator or a printer or a computer that has to work in the on ground, on earth. It's in a very comfortable zone or a comfortable atmosphere. You have an AC room and you don't throw it down, or it won't be subjected to a vibration, shock, vacuum and all. But in space, it's all very harsh environment. So this rocket has to pass through a very harsh environment, like extreme high temperature, low temperature. Then there are charged particles that can affect the some of the electronics, especially the semiconductor devices. And you have zero gravity. So zero gravity, when you keep a glass full of water, the water always stays on the bottom side. Think of taking this fuel in a tank, and if it is going up in zero gravity, there is no such bottom and all. It can float around. So once that happens, then you won't be able to exactly give the propellant to the engine for the firing in the right way. So you need always a pressurized system. Then when a deep vacuum, all this gas, entrapped gases in the material gets sucked out, and the property of the material changes. It becomes brittle, and many of the electronic devices and material can lead to damages. Then we have our own magnetic field of the earth. So then as you all know, the debris is something which you leave it there. We call it as waste on earth. So any object after its lifetime, for example, the terminal stage of a launch vehicle or a spent satellite, if you're not going to take it back to earth, it will stay there, and we call it as a debris. So the debris, it keeps on increasing the population. So then when you launch a rocket, then you have to ensure that the probability of your rocket hitting a debris is very less. So we do collision avoidance analysis and all. So now you understood, no? So it's very, very challenging to design and launch a rocket. Now, this particular slide, I purposefully put this slide to make you understand how risky the space travel is. Now, I have shown two photographs, one on the left side and the right side. Left side, it's a failure that happened in 1986, wherein a Challenger, it exploded about 10 to 15 seconds after the launch. And on the right side, everyone knows in 2003, our Kalpana Chawla also died in the Columbia disaster when it was re-entering the dense atmosphere. So the Challenger, this explosion happened due to a leak in the solid propulsion stage, and the culprit was an O-ring. The O-ring was O-ring is you can see this O-ring. It looks like a rubber band kind of thing. Maybe it is something similar to the gasket what you see in a pressure cooker. So after due to the aging, it loses the elastic property. It becomes brittle, and if it fails, then this hot gases, it leaks out through that sealing, and the moment it leaks out, it breaches the protection system, and it can lead to structural damage. So the point is that this O-ring may be costing 50 rupees or 100 rupees, but it can create disaster. Like here you can see 7 human beings lost their lives, and maybe around 1,000 crore mission. So this is the importance of every small or big component that is used in a launch vehicle. It should not fail. Now you have different orbits like polar orbit, geostationary orbit. Polar orbit, something the satellite, it travels from pole to pole, from North Pole to South Pole, and most of those satellites are used for this IIRS kind of satellite is for remote sensing purpose. And the availability of a satellite, that means when I say availability, that is the visibility of the satellite on our country, but that will be limited. For example, because it will be we will be able to see it for some maybe half an hour, 45 minutes, then it will again go away, then again it will come back after some time. So those orbits are low Earth orbits, typically around 600, 800, 900 kilometers. And the geostationary orbits is an orbit, what you see on the top left side, where the satellite rotates at the same speed of the Earth. So mv squared by r, or mr omega squared, balances mg. Mm cancels, g is the gravitational pull, then you can find out r. So there is a unique value for r, that is around 36, roughly 36,000 kilometers. So you put a satellite, then a man, it will, if you are positioning the satellite on our country, it will always stay there. So, but then the difference is that 36,000 is pretty long distance, and you have to overcome the gravity for a longer duration. So hence you require more powerful rockets, and hence you may require cryogenic stage, which I will explain in the subsequent slides. But just remember that to reach 36,000 geostationary satellite, you require powerful rockets. For such rockets, you may require cryogenic engine. Now this I've already explained. Now I will show some history, a bit of history. If anyone asks me what was the biggest invention in the last century, my personal opinion will be the invention of aircraft. That was in 1903 when the Wright brothers, Orville Wright and Wilbur Wright, they had a successful unpowered flight, powered flight for 59 seconds. So that was the beginning of a we can say as a new era of transportation, that is through the transportation through air. And subsequently, in the next 6 years, this aircraft kept on changing. These are some of the primitive instruments that was used at that time to find out the speed, time, and all. And when it reached 1910, it was even fitted with a machine gun. See, all human beings, the general tendency is to use a technology for the wrong sense. In many areas, it happens. So naturally, this aircraft, it took a center stage in the First World War. Until then, people used to fight physically, straight. They used to come on horses and with swords. But then, when in the First World War, aircrafts were extensively used especially for bombing. So those who had this technology got the upper hand. You can see a number of German aircrafts like Albatros, Fokker, Gotha, and then 2 British and 1 Newport French aircraft. Then after around 20 years down the line, The way in which the war was fought, that is the Second World War in 1939 to 45, it was in a different way. Although aircrafts were used, but mostly missiles were used after that. In between, in 1926, a man named Goddard, he invented a rocket by successfully test firing a rocket in 1926. Then, we human beings use that technology for in the Second World War. And you can, what you see on the right side is V2 rocket that used a semi-cryogenic engine in 1940s. So that is the kind of technology that was developed even at that time. So when the Second World War ended in 1945, a man named Arthur C. Clarke, he proposed an idea that if we can position objects on orbit, where the gravitational attraction, it balances the centrifugal force, then it will stay there, as I told earlier. And if we can have 3 satellites, then we can have a global communication coverage, which means a satellite, what you see on the 12 o'clock position on the bottom left figure, that can communicate can receive communication from Earth and send back communication to Earth. And then that satellite can also communicate with the other 2 satellites. So in that way, we can have a global coverage. That came in a magazine or a journal called Wireless World. That was in 1945. At that time, many people suggested it as a very crazy idea, because at that time, nobody knew how to take a satellite and position at this altitude. But after 12 years down the line, it became a reality. That Russians sent a satellite named Sputnik. Is the first artificial man-made satellite. Roughly the diameter was around 0.6 meter, and it stayed in orbit for close to 3 months. And it used to send a small radio beams, and it used to make beep sounds. So people used to tune to that signal and hear that beep sound. So at that time, it was people were very curious, and they were thrilled to get some signals from the sky for the first time in their life. But another thing happened is that you see the communication at that time was not to the extent what we have today. Like we didn't have any WhatsApp, Twitter, or television or mobile phones at that time. So this launch came as a big surprise for the Americans. So that culminated in the Cold War, means the technological war between the Americans and Russians. So what you see on the screen is a photograph of first achievements, like first probe to space, that is a Luna, by Russians. Then the Leica, the dog, they were the first. Then Yuri Gagarin was the first man to reach outer space. Then Valentina Tereshkova was the first woman. Then Alexei Leonov was the first man to do the spacewalk. Then finally, Americans had the last laugh in 1969 when they landed. Neil Armstrong landed on moon. Then after 1969, we can say that the Cold War ended. And bottom right side, you see a photograph where an American and Russian, they took a selfie or a photo inside the International Space Station. So now a lot of good collaboration is happening across the countries. Now, many of you may be thinking what India was doing all this time. And were we sleeping? Were we lazy? I don't think so. If you see the gross GDP, GDP is our gross domestic product, the value of that, what India used to produce was close to 1/3 on 1/4 of the total world GDP. Means we were a very rich country in 14th, 15th century. But then when the British left in 1947, our percentage GDP came down to just less than 3% or 3 to 4%. So we were struggling, and we were struggling to stand up after 1947. So we didn't have the luxury to even think about the space technology at that time. But then in 1962, a great man, a great visionary named Dr. Vikram Sarabhai, he had that vision, and he convinced the then Prime Minister, Pandit Jawaharlal Nehru, on the importance of India venturing into the space research. And in that way, the Indian National Committee for Space Research, INCOSPAR, was set up in 1962. So even though India, our nation, was struggling, we could start the space program at that time. So now, when you think back, that was one of the most important steps that that was taken in this field at that time. That's why where we are in a very comfortable situation, a very good situation right now. And how we started was it was the Tumba, a place named Tumba. That is where our my center, Vikram Sarabhai Space Center, is located in Trivandrum, was selected as the place from where the first sounding rocket can be launched. Why? Because the Tumba is very significant, because the magnetic equator passes through this Tumba. You have a North Pole, magnetic South Pole, and the equilibrium position, we call it as the magnetic equator, that incidentally passes through Tumba. So naturally, there was an increase in interest in knowing the atmosphere on this magnetic equator, especially on the charged particles. And that's why this was selected. And also it was on the coastal side, so that any small rockets that is launched, it will fall on the ocean. So because we cannot launch a rocket on the landmass. And how it started, because we didn't have much money, we requested the then church, which was a fully functional church, St. Magdalene Church, and requested them to let their space to us to start our space activity, and they were magnanimous enough to give that space, and we started functioning in this office, what you see on the left side. And now we use that space, that particular building we maintain as the Space Museum. So if you come over to Trivandrum, you will be taken to this Space Museum, or this church, what you see as a St. Magdalene Church. So we started sending small rockets called sounding rockets. Sounding rockets, some people think that it's a rocket which creates sound. It's not right. All rockets create sound. Sounding rocket, people say that the name came from a Latin word called sonde. Sonde is the meaning is to measure. So our idea was to measure temperature, humidity, pressure in around 8 to 10 or 15 kilometers. So we used to make small rocket sounding rockets, and we used to launch them. See what you see on this photograph. You can see this cursor. This is Dr. APJ Abdul Kalam squatting and preparing a sounding rocket before its launch. And then we started making small satellites, Aryabhatta, Bhaskara. We didn't have the rocket at that time. So we took the help of foreign launch vehicles to launch these satellites. And Apple, SROS is Rohini, then Stretch Rohini series is SROS. These are some of the early satellites. We depended on the foreign countries. Then we slowly migrated or started building from small sounding rockets to big sounding rockets. So you see on the extreme right is a very big sounding rocket which can climb to an altitude of 600 kilometers, not just 6 or 10 kilometers. So we were constantly working. Even now we continue to launch these sounding rockets. Then now with this confidence, we started building small satellite launch vehicles. And all these satellite launch vehicle, short form is SLV. and you might have, many of you may know this SLV-3. 3 means it had 3 stages, and all the stages used solid propellant. When I say propellant, it is a fuel. Solid means the propellant stays in the form of solid form, that is the solid state, just like the the gunpowder that is used for in small Diwali rockets. So it's a solid propellant, similar to that. But the petrol, diesel what used in the automobile is a liquid fuel. So this SLV used solid fuels, and the project director of this vehicle was Dr. APJ Abdul Kalam. Then after the first unsuccessful launch, then the second launch was successful. Then we migrated to augmented satellite launch vehicle by putting more solid propellant motors. We call it as motors. It's not engine. Basically, it's the engine. And made bigger solid rockets, which can carry bigger satellites. But then we understood that that alone, solid propulsion alone, is not sufficient to take meaningfully big satellites. When I say meaningfully big, means it should be around 1.5 to 1 to 2 ton kind of satellites to an orbit of 600 to 1,000 kilometers. We needed liquid propulsion system technology. So liquid propulsion, it uses liquid which stays in the form of liquid in the room temperature. So in that way, that we got the technology from the Viking engine. We developed the Vikas engine, and that was used in the Polar satellite. We had the first mission in 1993. That was again a failure, but then all successful mission except for one more in C-39. Every PSLV launch was a success, and it is one of the most successful launch vehicle in the world as on today. And then we understood that this liquid propulsion alone is not sufficient. We need still more powerful engines to take the satellites to geostationary orbit, which is around 36,000 kilometers. For that, you require cryogenic engine. Cryogenic is a field where it's a field where it deals with anything which deals with extreme low temperatures like -170 to -250 degrees Celsius. That is called cryogenics. So you require cryogenic engine, wherein the liquid propellant, typically it is a liquid hydrogen, and the oxidizer is liquid oxygen, so which has to be liquefied at -195 degrees Celsius, and liquid hydrogen at -252 degrees Celsius. And the technology is very complex, because if this temperature also has to be maintained. If the temperature crosses, then it starts boiling, it pressure rises, it can lead to explosion. You should have very good thermal system, good very challenging material selection design. So it is a very complex technology. But then the advantage is that in a layman's language, we call it as mileage. But in rocket engineering, we call it as specific impulse. Means specific impulse is the force an engine produces for unit weight flow rate of the propellant. So this specific impulse for a cryogenic engine is more than 2 to 2.5 times that of the almost 2 times that of the solid propulsion. So that is the benefit. That means it for the same weight of the if you compare a solid propulsion system and the liquid cryogenic propulsion system, cryogenic roughly produces double the thrust, and hence it can go to a higher altitude. Now, what you see on the extreme right is GSLV Mark III. We call it now as LVM3, Launch Vehicle Mark III. This is the most powerful rocket what our country has built today, and we have used this rocket for our Chandrayaan mission, and we also have we are going to use, and we also use this for launching OneWeb satellites recently last year, and we are planning to use this vehicle for our Gaganyaan mission. Gaganyaan means taking human beings to outer space, for which we have completely redesigned this engine, because when the moment you are putting a man inside the rocket, then you need to have fault tolerance for the vehicle. Means with one failure, we cannot lose the lives of a human being. So that means the electrical and electronic system of this human-rated launch vehicle has to tolerate failures. Now, this I've already explained. Now, I will come to the different types of launches. Everyone knows that rockets are or can be launched from Earth, from ground, land mass. But then some countries, they launch from the sea, right from the middle of the sea as well. Why? Why? Because you imagine a person, this is a very important point I'm telling, a person, you imagine a person standing on the pole with that you can see, sorry, you can see on the cursor here, somebody standing here, he will rotate about his own axis, but that means he's not moving linearly. But imagine a person standing right on the equator. So he is moving with, he is rotating around the earth at a velocity r omega. So that r omega, the linear velocity of that person standing on the equator is around 1,650 kilometers per hour. So a normal aircraft, a jet, a Boeing 737, it travels at around 800 to 900 kilometers per hour, which means a man standing on the equator, already he is traveling with double the speed of a jet aircraft. That means if you are going to launch a rocket or a launch vehicle right from the equator, it will have an initial velocity of 1,650 kilometers per hour. That means you need to only impart extra velocity that taking the satellite to the required orbit. Now I'll show you a small video on such a launch. Why they are taking to ocean is, if some in some countries they have if they have a sea mass where the equator passes through it, then yeah, that is the best location. So they take it to the equator, so right in the middle of the ocean, and launch it.
Dynamic positioning system acts like an anchor, holding the platform in, and the hydraulic arms of the transporter erector push it into ready position.
So that is sea launch. Then if some people think that whether can be launched from air, what is the need? Suppose if the rocket is very small in size, then we can also think of taking this small rocket, fitted to the belly or bottom side of a typical aircraft, and take it to a altitude. Typically an aircraft, it flies at around maybe 10 to 15 kilometers or even 20 kilometers, and then you can launch the rocket from there. So you will get that advantage of that extra height gained. So I will show you such a video of an air launch. So that was sea launch for you. Now I think many of you may now appreciate the fact that our launch pads, which is at Sriharikota, is very close to the equator. So we have that advantage of the initial velocity of close to 1,650 kilometers per hour. Now, how do you control the rocket? Because once you launch, then you need a steering system. Just like how do you ride a bicycle or a bike? The person who is riding holds the handle with using his hand, right and left hand, and always he does the balancing act. So basically, he's trying to shift the center of gravity of the vehicle to left and right to keep the vehicle stable. So such a balancing act is required for this rocket as well. It is, you can imagine that you are holding a long stick and trying to balance. So you have to always impart a lateral force to counter the falling moment. And that is called control, to keep the vehicle stable. Then you intentionally, you may have to change the direction of the rocket. How do you do that? So that is by altering or changing the thrust direction of the thrust. Thrust is the force with which the rocket is propelled upwards. So you just see on the bottom left side, the nozzle through which the hot gases comes out is gimbal or moved to left and right or to and fro using mechanism called actuators. It is like robotic arms which will push and pull the nozzle. So when the nozzle is moved, this thrust also gets altered. Due to that, the direction of vehicle movement of the rocket also gets changed. Incidentally, I am working in such a group of designing and developing actuators for this launch vehicles. And what you see on the bottom right side is a photo typically of a launch control center. And if when I go to schools and colleges, many students have asked this question, that what these people are doing there, how they are controlling this rocket which is going at very high speed. The answer is they don't control the rocket, and it's impossible to control a manually control a rocket which is going at a speed of around 8 to 10 kilometers per second. That's not possible. So many of these people, or 99.9% of these people, they only just see what is coming out of the vehicle, that is through the data. That is, every person is maybe responsible for developing a system. For example, an electronics or a mechanism or the propulsion system or the structure. So and this rocket will be completely instrumented by putting sensors to find out the performance or the health of the system which they have designed. So probably they will be continuously seeing, not probably, they will be continuously seeing the health of the vehicle before the launch and during the launch. But one person has the control over the vehicle, and he presses a button which can destroy the vehicle. Because if the vehicle, due to some mistake, if it ventures or goes out of the path, then you have to press that button to destruct the vehicle. We call it as a safety corridor. Because otherwise, if you don't do that, this vehicle, if it gets launched from this Sriharikota, and if it, due to some mistake, if it changes its direction and come back to Earth, imagine that this rocket falling on middle of the Chennai city, it will be very disastrous. So the moment it crosses the safety corridor, a person on ground can issue a telecommand system to destruct the vehicle. Now, this slide I'm showing to get a feel of the size and weight of the vehicle. What you see on the left side is a 12-story building, a flat, typically an apartment, and our rockets are much more taller than that. And the weight of a rocket, you just see the LV-M3 rocket on the extreme right, it is equivalent to around 500 cars. 500 cars. So, and this GSLV is around 350 cars, and PSLV is around 250 cars. So now you can imagine how big it is. And see the weight of the payload, that is the satellite itself, is 8 cars for GSLV. Now, these are some of the photos that was typically taken in the launch pad. Just like what we build a building, first you make the foundation, make the ground floor, then first floor. The rockets are also built like that. First you start from the first stage, then you put this second stage on top of that, and then what you see on the green color is the mobile launch pedestal, where on that people can stand and work. And once that integration is completed, that pedestal can be folded. You see on the left side the pedestal is on the right side the pedestal is folded, which means the vehicle has been built completely and it is ready to be launched. So this we call this is the vehicle assembly building, VAB. And what you see on the on this is a big rail, and on the extreme on the front you can see an umbilical tower. That is a launch pad. So this is around roughly half a kilometer. The vehicle is slowly, it moves on the rail with a velocity, with small speed. It takes half a day to reach half a kilometer. And this is the typical the specific impulse of rockets. I told you what is specific impulse. It is the thrust by weight flow rate of the propellant. So a cryogenic engine, it roughly gives 450, the unit is in seconds, 450 seconds, and the solid propellant is 250. Semi-cryogenic means one of the, like liquid oxygen is in cryogenic stage, but the fuel instead of liquid hydrogen, we can use kerosene. It's not the household kerosene, but is refined multiple times. We call it as the ISRO. That gives a specific impulse of between the cryogenic and the earth-storable engine, liquid engines. And this is the mission and launch control center in our Sriharikota. It is roughly around 10 to 12 kilometers from the launch pad. So a person standing on this balcony can directly see the launch through his naked eyes. And I don't have to dwell, probably you might have had other presentation as well on the kind of uses of the satellites: telecom, banking, internet, TV, GPS, shipping, mapping, weather forecasting, global internet coverage. So think about anything. Now we have reached a stage where we cannot think of a world without a satellite. Now, all these rockets, what I have explained, are called expendable rockets. Expendable is it after each stage burns out, it is thrown out to the ocean. And finally, what is left over is a final terminal stage and then the satellite. But the problem or disadvantage with that is that the vehicle, we loses the vehicle. So can you ever imagine that if you have a car and you are traveling the car and leaving the car there at the destination and coming back alone, you will lose the car. So every time, so it becomes an expensive affair. So to reduce the launch cost, we need vehicles which can be reused. Means after injecting the satellite, it can come back and fly like the space shuttle. Probably you may be knowing that Landis, the Challenger and the Columbia space shuttles, just like that. So we also have developed such a reusable launch vehicle. We had a successful mission recently, about 1 month back, also on the autonomous landing of this RLV on a runway in Chitradurga and Karnataka. So that was the second mission, and the third mission we are planning at the end of this month. And ultimately, we want maybe within the 1 year or 1.5 years, we will be launching this to an altitude of around 400 kilometers. It will stay there. After injecting it, will stay there. For maybe 5 to 6 months, we can do multiple experiments in the zero-G environment, just like the experiments what we conduct in the space station, and then it comes back, re-enters the atmosphere and land like a normal aircraft. Chandrayaan mission, I don't have to dwell. This is the rover, what was used in the Chandrayaan mission. Lander, it landed, it had 4 missions. Basically, from the launch vehicle perspective, I will tell you, this is an interesting slide. See, we took a trajectory wherein the launch vehicle, it injected the payload to an elliptical orbit. So every time the farthermost point is called the furthermost point in the orbit is called apogee, and the nearest point towards the Earth is called the perigee. So every time you reach the perigee, you give a firing. Means an engine is there, it gives a firing for a prescribed duration, so that the ellipse keeps on growing. So after each firing, this ellipse keeps on growing, and finally, after it reaches a very large orbit, then you give the final firing, which will take or escapes, which will enable the spacecraft to escape from the gravitational pull of the Earth, and finally, the moment it reaches the moon's near the moon's gravitational sphere, it gets attracted and gets into an orbit around the moon. And from the moon, using various phases like rough braking phase, how do you do the braking? You reverse the thrust. That means you imagine that the thrust is given towards the front side in the direction the vehicle is going. That means it reduces the forward velocity of the vehicle. The moment the forward velocity comes down, then the gravitational pull will overcome the centrifugal force. So the altitude comes down. That is called rough braking, and then the precision braking phase, and finally it becomes vertical, and through a controlled firing of the engine by keeping a thrust just almost equal to the weight of the craft, it can be brought down in a controlled way, and we can land with a sink rate of less than 2 meters per second. So that's how we landed on moon. And I told that we are planning for a Gaganyaan mission, that is human in space mission. So for that, we require a special capsule. We call it as a crew module. The crew is a person who travels on board a launch vehicle, and this cabin has to have a full environmental control and life support system. That is, we call it as an ECLS system, where the atmospheric pressure, the temperature, the humidity, everything has to be controlled in a very tight, narrow band, which makes it comfortable for the crews to stay there. Otherwise, imagine we cannot stay beyond 35 degrees or 40 or 45 degrees. So it has to be the temperature, all this will be nominally it will be around 24 degrees, relative humidity and oxygen, partial pressure of oxygen, all these things are important. So all these systems are getting developed. So this crew module, this service module is a propulsion part that is on the bottom side, and there is communication between the crew and the service module. There is coolant system, a lot of complex system. I'm not going into details of that. So our mission, and this particular module sits here instead of the satellite. And this module is injected into around 400 kilometers orbit. That is where the International Space Station is. Around that orbit, our plan is to spend around 7 days in space, and there's a capability of 3 astronauts. We call it as a Vyomanauts to fly in this vehicle. So they stay in this position because the upward acceleration, if this person is staying upright or sitting upright, then due to the acceleration or the forward acceleration of the vehicle, it passes through our vertebra. That is not good, no. So it is always better for our health to lie down, so that the force, the forward acceleration force, inertial forces, exactly it acts perpendicular to the vertebra, so that we will stay healthy. And this is my last slide, a very interesting slide, because every time I make a presentation, I love to show this as his last slide. So a person who is staying, maybe I know that all of you might be staying in right from north to south and east to west of this country, and the moment you are asked to go when you are trying to get a job or to study further. You may have to leave your hometown. You become homesick. But the moment a person is getting transferred, or he has to go out of his state, or his first ambition or his desire will be to come back to his home state. If it is Delhi, he may try to come back to Delhi. But imagine if he has to go out of the country, then he becomes homesick, and he will say that somehow he wants to get into come back to our country, and he can stay anywhere in the country, he won't mind. But think about a person who is going away from the Earth. So this question has been asked to many astronauts and many people who went to the outer orbit, and he or she, after staying there for months, maybe up to 8 months or 9 months or of 1 year, when he looks on Earth, he feels that he becomes homesick, and he feels that he wants to come back to Earth and is ready to stay anywhere on the Earth. We are all one and the same, and we make divisions and make different countries and continents, but then he gets the feeling that we are one and the same. So with this, I end my presentation. Thank you very much.